Hi friends, today we begin lecture 18 in our course and today I'm going to talk about the airfoil section. Though we have periodically discussed the airfoil every now and then as the typical wing section, today we are going to formally look at all the different notations which are relevant to the airfoil. Let's begin. So if we look at a typical aircraft and wing section, we'll see something like this. So in an aircraft, you have the nose, the fuselage, the cockpit where the pilot sits, and then you have the wing, which is the part of the aircraft which typically generates lift, which is required to sustain the aircraft in the air. Now, if we cut the wing at any section, we will get a cross section which looks like this, which is typically called the airfoil section. So you're not going to get a rectangle section here, you're not going to get a cylinder, you are going to get an airfoil section. Now the airfoil section looks something like this. There is a sharp trailing edge, there is a smooth leading edge, and then the airfoil is typically thicker somewhere in the middle or near the quarter chord, and it's typically thinner towards the trailing edge or sometime toward the leading edge. So essentially, this airfoil section has come up over many years as the proper cross section to have for an aircraft wing because it tends to generate a high amount of lift and a relatively low amount of drag. Now, essentially, we call the front of the aircraft the leading edge or the front of the airfoil the leading edge. That's where the velocity is coming, and the end part the trailing edge. So that's the place where the velocity goes off or the air goes off. So now let's look at the cross section in more detail. So here I have given an expanded view of an airfoil cross section in yellow. So again, this is the trailing edge, this is the leading edge, you have the upper surface, you have the lower surface, and the distance from the front to the back of the aerofoil section, this is known as the chord or the chord length, and it's typically denoted by the letter C. One more important location is the quarter chord. So it is at the location C by 4 from the leading edge. Now, if you join the leading edge and the trailing edge, you get something known as the chord line. And relative to the chord line, there is another line called the mean camber line. And that is the line which is equidistant from the top and bottom surfaces of the airfoil. So we can see this is a center line of the airfoil cross section here, and so this distance is known as the camber. So it's essentially the deviation which the airfoil has from a symmetric cross section. So in case we have a symmetric airfoil, the camber is going to be 0. So that's something to keep in mind, that certain aircraft, for example, if we have helicopter rotor blades, you essentially use a symmetric cross section there. But in general, for many aircraft, you will have a cambered airfoil. So now let's take a look at this airfoil section when it is at an angle to the wind flow. So essentially we have the flow velocity V in this direction and the chord line is here, and I have this angle to the chord line. This angle is denoted by alpha, the Greek letter, and it's also known as the angle of attack. And now we can think about this airfoil section, we can think about this flow, and what's going to happen is that there is going to be a force and a moment generated on the airfoil section. So if we consider the quarter chord location, you will typically have a force R and there will be a moment mc by 4. Now what we do is that we resolve this R into two components. One is parallel and one is normal to the direction of the velocity. So the component which is normal to the velocity, that is called the lift, denoted by L, and the component which is parallel to the velocity is called drag, that is denoted by D. So these are two very important things to remember as far as aircraft are concerned, is that the lift is a force which acts normal to the velocity and drag is the force which acts parallel to the velocity. And of course these are both forces, so the unit here will be Newton. and for the moment the unit will be Newton into meter. Now, what would happen is that if you chose a different location for this particular moment, you are going to find that this moment is going to be different. So, the moment varies based on the point about which it is taken. So, in general, if we take the moment about the leading edge here, it's not going to be the same as the moment at the quarter chord. And in general, any of these moments are going to be functions of alpha. So, as we keep changing alpha, the moment is going to change. But fortunately, one thing which happens is that there is a certain point in the airfoil where the moment is not going to vary with alpha. And this point is known as the aerodynamic center, or the notation AC is often used to denote this point. And this point is fortunately located at the quarter chord for low speed subsonic situations, and we can essentially say that MAC is going to be constant because that's the way you define the aerodynamic center. So remember this very important fact that if we have an airfoil of chord C, then the quarter chord location from the leading edge, that's the point where we typically have the aerodynamic center for a typical subsonic airfoil. Now, we have only discussed a few type of designs here. Many possible designs are possible for aerofoil sections. So for example, we have a conventional airfoil section. We have a laminar airfoil section, which we have seen before. Laminar airfoil section has the maximum value somewhere at mid chord. You could also have a laminar airfoil section like this. Now, this is a cambered section. This is somewhat of a symmetric section. The laminar airfoil section, they were not very successful for laminar flow because, as I mentioned before, often the flow would separate, but they are actually good for high speed flow and supersonic flow. So in supersonic flow, we sometimes have a wedge type of airfoil section, or we can also use something like a laminar section there. Also, there is the possibility of using something as simple as a flat plate as an airfoil, typically at lower Reynolds number, for example. And for very small aircraft, we could also have different type of sections here for different small aircraft and so on. So what we are familiar with most of the time, the typical airfoil sections we see, these are for high Reynolds number type of situations of about 1 million or so, where most of the aeroplanes fly. And if you are in different flight regimes, the airfoil section is going to be different. So let's summarize this lecture today. We saw that the airfoil cross section is good for generating high lift for a wing, and also I should mention that it's good for generating high lift and low drag. So that's something to remember. Also, we saw that the angle at which the airfoil is pitched is going to play a very big role in terms of the forces being generated on the airfoil. So as this angle goes up, the forces go up until a certain point, after which the forces start going down. For example, lift will start going down, but drag will start going up, and so on. That is the phenomena of stall, which is caused by separation. But if you consider the angles between say 0 to 10 degrees, generally you are going to get a good behavior during that point, and you are going to get linear changes or relative constant changes in all these phenomena. Now, we also saw that lift is a force which is normal to the airflow. That was very important. So it is perpendicular to the direction of the velocity, and drag is a force which is parallel to the airflow. So again, both these lift and drag are forces, so we can express them in Newton as the case is generally there. Now, further continuing on our summary, we saw that there is a pitching moment which is present, which essentially tries to roll the airfoil section downward or upward, and this is typically measured about the quarter chord. It could also be measured at the leading edge or at any given point, but quarter chord is often used. And we also saw that there is a certain point known as the aerodynamic center, and if you take the pitching moment about the aerodynamic center, then it does not vary with the angle of attack. We also see that for subsonic airfoil, the aerodynamic center is located at the quarter chord. So this is something which will often simplify our life dramatically. If we are in supersonic situations, the aerodynamic center moves up to the mid chord region. So that's something we'll probably look at later in this class. So basically today's lecture we had a formal introduction to the airfoil. Like I mentioned before, airfoil is a cross section which has evolved over 100 years, and it's a very suitable type of cross section for generating high lift and low drag for airfoil sections typically. So most of the time you can actually design an airfoil section to have maximum L by D ratio or something like that. And there are actually tools to design airfoil. For example, there is a software known as Xfoil. So if you search in Google, you are going to get more information about the airfoil design problem itself. I'll end this video here and I will see you in the lecture sometime soon. See you then.